Hello everyone. Welcome to the Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IASC. It's my pleasure to introduce today's speaker, Professor Vincent. He will be speaking on BanditSpec, adaptive speculative decoding via bandit algorithms. Professor Vincent received BA and Master of Engineering degrees in Electrical and Information Science from the Cambridge University in 2005 and PhD degree in Electrical Engineering and Computer Science from the Massachusetts Institute of Technology in 2011. He is currently a professor with the Department of Mathematics and Department of Electrical and Computer Engineering, National University of Singapore. His research interests include information theory, machine learning, and statistical signal processing. Audience is encouraged to ask questions at any point during the talk. For those attending online, questions can either be asked by unmuting or speaking them directly or typing them in the chat box from where they will be relayed to the speaker. Over to you, Professor.
All right, thank you very much for the very kind introduction and for inviting me to this seminar series. I had the great pleasure of meeting many old friends and making new friends here in IISc. I know many people here, and it's also very nice to meet new people. I see that there's a lot of interest in areas of common interest, like multi-armed bandits, information theory, reinforcement learning, and so on. So today I want to talk about a relatively new work on an application of bandits to large language models. So when we talk about bandits, when we write our papers, we usually motivate bandits using a couple of well-known applications such as online recommendation systems and clinical trials. So I was just talking to a few people this morning. It is not so clear whether bandits is actually used in clinical trials or not. That bandits is used in recommendation systems. We want to explore the frontier of bandits and we want to understand whether it can be used somewhere else. And one of the places that we are trying to use bandits is in this area of large language models and enhanced inference. And I cannot claim that our solution is already out there and being used in large language models, but I want to see bandits as a viable step to help in enhancing inference in these language models. So this work is titled BanditSpec, Adaptive Speculative Decoding via Bandit Algorithms. And it's really about using bandits in speculative decoding. In case you do not know about speculative decoding or you do not know about bandits, I will explain so that everyone has some idea about what I'm talking about. So this work is done mainly by my students, Yun Long, and who work on the theoretical aspects, but in order for us to be able to implement this on systems, we needed industrial collaborators. And these are industrial collaborators at some AI labs in Singapore, including C. We also had some other collaborators from the Singapore Management University and Yale. All right, let me now go into decoding. What do we mean by canonical decoding in language models? So in canonical decoding, tokens are generated in what we call an autoregressive manner. Each token requires a full forward pass through the massive target model. A target model is nothing but a conditional distribution from the set of all finite length strings over a finite alphabet, set of all tokens, to the probability distribution over that alphabet. So that's nothing but a conditional distribution. How does it work? All right, let me walk you through this and then provide you with an example later on. One is given a prompt, let's call it PT. This prompt is nothing but a finite length string in the alphabet. One is also given a target model, which is this large language model. And this large language model takes in the prompt and produces a probability distribution over tokens. So what does it do? It first starts off with the beginning of sequence. You will see BOS quite frequently later. So while we are not at the very end, we will increment and we will produce a token given the previous prompt and the large language model P. So the next token XT will be sampled from this conditional distribution. What happens is very simple. Concatenate the produce token with the previous prompt to form the next prompt, PT. And then this process will continue until the end of the sequence. What we will return at the very end is the canonical decoding time tau c, as well as the produce sequence of tokens at the canonical decoding time tau c. It's as simple as can get. It's just nothing but running an autoregressive model using a particular target model P. Yes?
So how is EOS defined?
Well, EOS is basically the end of sequence. It could be the number of tokens you want to generate, like 10. It's just defined whenever you want to stop the whole production process. So it looks like this. We have a beginning of the sequence S, and then what we will generate is, well, we have a first empty prompt, and we generate this the word adaptive, and then the word adaptive will be the prompt at this particular point in time, and the word adaptive will be then passed into the large language model P. It will produce the next word, which is speculative, and so on and so forth. Oops, I'm sorry. So what happens here is you need to calculate the total time that is taken to produce this entire sequence of tokens until the end of sequence. The end of sequence here in this case is, I don't know how many words here, 11, okay? So if we use a model such as LLaMA3 8B, which means 8 billion parameters, then the target, each token will require us about 30 milliseconds to decode or produce. So by a simple calculation, the total time required to produce 11 tokens is about 330 milliseconds. Now this is too long. So the main question we want to address in this work is, how can we accelerate this one-by-one token generation process? Is one-by-one token generation process using one single large target model the right way to go? Obviously not, because we have a more sophisticated way to do things. So this brings us to the topic of speculative decoding, which is a work that was initiated by 2 groups in Google in 2023. The key idea here is that we want to accelerate inference of large language models while maintaining the high generation quality. High generation because the target model P that I talked about was a large language model. It is expensive to train. It produces tokens of high quality. We want to maintain that, but we want to dramatically reduce this generation time. So speculative decoding involves 3 steps. One is draft, second is verify, and third is accept. And I'll try to explain these elements in the following. So we assume that we have a certain draft model. This is a small model, such as T5 with 77 million parameters. Compare that to 8 billion parameters just now. Significantly less. So we assume that we have this draft model that is quick to generate, quick to draft tokens. So we're going to draft the next L, say L is a fixed number, of tokens via a draft model autoregressively. So this is very much similar to the target model just now. So we are going to draft a bunch of tokens based on the previous prompt and based on all these drafted sequences up to time j. Now, these draft models are small and fast and may be inaccurate. Let me try to pass this for you because I didn't explain this very well using this example. So the draft model produces all the stuff in, or drafts all the stuff in green. For example, if you already have the first 3 tokens here, the draft model may suggest these other tokens. All right, these are relatively cheap to produce, but it may be, those tokens may be inaccurate. Okay, so it looks at the previous the prompt previously and it produces via. It looks at the prompts previously and via and the word suffix and so on and so forth. But this may be inaccurate. So what we will do is we will use the large model T to verify the drafted tokens. i.e., what do we mean by verify? We want to compute the probabilities of the outputs via the large language model in parallel. So these probabilities can be computed in parallel, and based on the probabilities, we will accept or reject what the draft model has drafted for us. We of course hope to accept everything, but because the draft model produces tokens that could possibly be inaccurate, we might have to reject. What is the criterion for acceptance or rejection? We will accept the draft token sequentially. There is a certain formula to acceptance of the draft tokens, depending on the quality it has based on the queue that generated it. Let me walk you through this formula. All right, so we will accept the drafted token with a certain probability. Now, if you look at this formula here, if P is larger than Q, that means the token is good, because the probability under the target model is high relative to the draft model. So if this ratio here is bigger than 1, then we will certainly accept it. Yes? The probability of computing the length of the input token. Yeah, it depends on, this conditional probability depends on all these previous tokens, right? Yes, possibly. Okay, so each one of the costs here we assume is the same. Yeah. Yeah, irrespective of how long the input token is. Yeah. So there's another question here?
Something. So I thought that it's easy to sample by the distribution, but you do not know the probability distribution itself, right? Because the alphabet, the next token is very, very large, right?
Yeah.
So you'll have to know the probability for in all possibilities there, right? The distribution is over the entire alphabet, right?
Yes.
The next token. Is that what you're going to do? Or because it's easier to get the sample from the distribution rather than knowing the exact distribution. What I meant is that if you run a small model, right?
Yes.
It's easy to get what the next token will be, right? With some randomness rather than knowing what probability you're outputting.
Yes, that's right. But to compute the probability requires some time.
So you need to actually know the probability.
Yes, yes. But once you know the probability, you will be able to compute this ratio. If this ratio here is bigger than 1, then you certainly accept the token. If this ratio here is close to 1, P divided by Q is close to 1, then you will accept the token with high probability. But if the probability of the generated or the drafted token is much smaller than 1, it's very likely for you to just throw the drafted token away. So, an example, adaptive speculative decoding, okay, this is going to be accepted because the probability is, for example, high or bigger than 1. The probability is high or bigger than 1. Okay, so what we'll do is we accept the drafted tokens until the first rejected one. For example, the one in is going to be shown here. So this here it has, for example, low P probability. And so we're just going to omit it. And we're going to, once we omit it, we cannot stop there, right? We need to correct it. So we're going to correct the red token that was rejected by generating another token here from a function of the target model and the draft model using this formula. So in this way here, what we have is a sequence of operations which is draft, verify, and accept. So for example, if we are given this input string here, we first generate this draft. And then we will verify these generated tokens. A particular formula here, the minimum one and the ratio, to accept or reject these tokens. Once we have accepted, we keep it. And once we have rejected, we correct it using the target model. Okay, we save a bit of time because this particular token here was generated, or was rather drafted using the draft model, and draft models are small, and so this requires negligible time compared to if it were to be generated by the target model. So as you can see from this table here, we are going to compare canonical decoding with speculative. Canonical decoding is just the picture, right? Canonical decoding requires 11 runs of the target model, but in this particular case of a toy example, we only require the draft model to be used a smaller number of times, basically to do this correction here. So there is some benefit in using drafting in tandem with the presence of a target model. So let's just do some simple calculations to motivate the definition of our regret, all right? So for one round of speculative decoding, you need to use this number of steps. The time you need to draft plus multiplied by the maximum number of tokens you need to draft is the L. The target model to verify. And then this because the target model is large, so it dominates this entire calculation. What we are concerned with is and the metric that we want to try to optimize is the total time saved. This total time saved can be computed as follows: the target time multiplied by the expectation of the difference between the number of canonical decoding rounds and the number of speculative decoding rounds. This is the thing we want to maximize because we want to save as much as we possibly can. Now, because of the way the formulas were designed just now, as I described, the distribution of the generated token sequence is unbiased in the sense that the prompt or the sequence that was generated at the end of the speculative decoding steps is exactly equal to the prompt or the sequence that is generated by canonical decoding. All right, so we don't lose anything in terms of the quality of the generated token sequence. All right. Okay, so let me try to motivate why we do what we do in the following. All I've talked about up to now is what is speculative decoding. Now, not all existing speculative methods use a fixed configuration. What that means is that they have a certain target model and they have a certain draft model. P and Q are fixed. A single draft model or a set of hyperparameters is used for all tasks. This is suboptimal because the ideal configuration could depend heavily on the specific context. As I've talked to some of you this afternoon when I met you, right, these are two canonical examples in which the draft model could perform very differently because the settings are very different. Now, in code debugging, this is a particular task that requires precision, right? A small little error in this task could lead to catastrophic failure that your code cannot run. So a retrieval-based method like suffix tree might be the best. So what this means is that there is some queue that works well for this task. But if you're looking for a task that requires creativity, like generating the next Harry Potter, then a smaller draft like might be better. A priori, we do not know what the prompt is or how to adapt to the prompt. So question then is there any training-free method that can adaptively choose the hyperparameters such that the latency of speculative decoding can be minimized? All right, such that we can maximize the total time saved here. All right. So as you can see, there are different tasks, and a single draft model might not be optimal for each one of these tasks. So this calls for some form of exploration and then exploitation in order for us to choose a good draft model depending on the task. Okay? Now, this set of slides was designed for people of general audience, but I know that people in this audience know about bandits. Nevertheless, I will go through the dynamics of multi-armed bandits. And this is also to facilitate the further discussion of the criterion, which is the regret, that will look slightly different in our context relative to the standard regret. Okay, so in multi-armed bandits, as you know, we have a certain number of arms, say finitely many, and a certain given horizon T. So in multi-armed bandits, the agent adopts an algorithm, ALG, to select an arm IT based on the history. The environment reveals a reward to the agent. The history consists of the sequence of arms that was chosen as well as their corresponding observations. As we know, we want to, in the usual case, devise an algorithm to minimize the cumulative regret. So this is the best you can do. This is what you do based on your algorithm. All right, so multi-armed bandit setting. All right, how do we look at the problem of canonical decoding with many possible hyperparameters or many possible draft models as a multi-armed bandit problem? Here in this picture, I have two different arms. These two different arms correspond to two different draft models. I said just now that for the task of code debugging, all right, suffix 3 might be good. This is one of the draft models. For storytelling, eager2 might be good. So here are two different draft models. So they produce, they also go through a sequence of steps. As I mentioned, every draft model does a few things: draft, verify, accept. All right. So this draft model drafted the following. All right. And the acceptance probability is 2/3. This draft model drafted some words here, and the acceptance probability is 1/3. So our large language model here goes through this collection of possible draft models. Here there are 2 and here there are 4. All right, but there's a fixed number of draft models. And the question he asks is, which model should I choose? So we regard each candidate hyperparameter configuration, for example, draft models, as an arm in a multi-armed bandit problem. But I want to note that there could be other types of hyperparameters beyond draft models. In our experiment, we also consider the situation where we only have one draft model, but we can vary other types of hyperparameters within a single draft model. But for the sake of discussion, let me just talk to you at this point in time about hyperparameter being a particular draft model, which is corresponding to an arm in a multi-armed bandit problem. Okay? So we are going to marry these two together, these two notions that you are probably familiar with by now: speculative decoding and multi-armed bandits. But one thing I have not mentioned to you is, what is the notion that we want to optimize when we consider using multi-armed bandits on the speculative decoding problem? Let me talk to you about our BanditSpec framework, and it will then lead to the definition of it will then lead to a unique definition of the regret in our setting. All right, so BanditSpec is a training-free and adaptive online learning framework for hyperparameter selection in speculative decoding. Let me walk you through each of the steps. All right, when we are not at the end of the sequence, okay, then we will do the following. Okay, that we have a certain arm selection algorithm that we will design. We have an initial prompt, let's call it PT0, and we have a bandit configuration. What is a bandit configuration? It consists of a few things. It consists of 1, the target model, which is large. It consists of a few hyperparameter configurations, which you can consider as k different draft models. Say 2, all right? It consists of L. What is L? L is the maximum length of a generated sequence. Okay, an upper bound of generated sequence. Okay, so for example, let me go back to make this clear. For example, here, L is equal to 4 because it drafted 4, 1, 2, 3, 4 tokens here. But this is another hyperparameter. It's a maximum length of the generated sequence for a particular draft model. Okay, so that is a bandit configuration. What we don't know here are basically these rewards in some sense of the draft models. So while we're not at the end of the sequence, we will select hyperparameter index, which basically corresponds to one of the K draft models. And then we will receive the accepted tokens from that particular draft model. See, once we select a hyperparameter, just like in bandits, we pull the ITF arm. Here, we employ the ITF draft model. All right. Once we employ the ITF draft model, we pair it with the target model and the maximum length of the generated token sequence based on the previous prompt PT-1. And we then receive the accepted tokens and we concatenate that into the next prompt and the history. Then what we will do is we'll output the number of calls to this speculative decoding subroutine. That is what we call the ST, or the stopping time. Yes. L is fixed in our framework, but there is something related to L that we will vary very soon. L is fixed. Think of it as 5 or 4. All right. So this is the stopping time, which is the number of calls to the speculative decoding subroutine. All right. So one property of BanditSpec, regardless of whatever algorithm we use, is the following. We still have this preservation of the distribution property. At the end of it all, if we decoding, this is the prompt distribution. Is what we obtain through BanditSpec. As follows. All right, the length of the generated token sequence, upper bound and lower bound, and L is, as I mentioned. These two statements basically say that the token sequence is not compromised by our bandit algorithm, just as in speculative decoding, and the stopping time and the length of the generated token sequence are equal up to a constant factor. This brings me to the objective of what we want to do analytically. We want to devise an arm selection rule, ALG, stands for algorithm, to minimize a new notion of regret, which we call the stopping time regret. All right, so let me walk you through some of these terms here. This is the expected number of speculative decoding rounds for your algorithm to stop. Remember, this is the figure of merit, the stopping time. The other term is the expected number of rounds to stop if the Oracle best hyperparameter is adopted. So I star here, you can think of it as the arm. But here, this quantity ST is slightly different from the usual quantity we have in the regret. Right? The regret is basically the sum of all the rewards up to a certain fixed time. So this guy itself is a certain variable. Okay? So one can regard this blue term, which is regret, as the number of wasted or additional rounds. Okay? So the desired result that we want to try to prove is that the regret is either smaller than the expected length of the prompt, or based on canonical decoding, or significantly smaller than the expected length of the stopping time based on canonical decoding. Right, so these are some results that we aim to show, but more importantly, what we want to do is to make sure that the regret here is also small in empirical experiments, or the mean accepted tokens is larger than what we can expect if we use a single draft model or a single hyperparameter configuration. Let me walk through some analytical challenges in our framework. So here, there is another source of uncertainty, the stopping time, in addition to arm rewards in multi-armed bandits. In standard multi-armed bandits, the regret is just defined as a sum of the rewards that you accrue during the entire horizon. For instance, if we know that there's only one accepted token at each round, the stopping time is given by the length of the generated token sequence based on canonical decoding. This depends on some target model also has, because the target model itself is a conditional distribution. Now, the stopping time also depends on the generated tokens. Mathematically, this function here is a function that maps the generated tokens to the decision, which the agent does not know in advance. All right. So this function is basically mapped to from the set of finite length strings to stop or continue. So it needs to decide whether you stop or continue. The tokens are generated in an auto-regressive manner, and thus we don't have the IID assumption that we usually have in canonical bandits. So to make some simplifications to the problem. So for the first problem, we need to come up with anytime algorithms. Of course, these are available in bandit theory. For the second, we need to devise some martingale arguments to make sure that we can overcome this sort of stopping problem. The third is we need to come up with either assumptions or slightly different settings in order to deal with the automatic nature of the generation process. Okay. So what we do is we look at a certain stochastic model with some assumptions. It's an unreasonable. We also look at an adversarial model in our problem. I'm going to make these precise. So when we look at the stochastic version of this problem, I have one algorithm. I'm going to design one algorithm. Yes.
Yeah. So now you are choosing between different draft models. So that you are choosing. Are you choosing in the beginning of the query or at each?
At each time, just like in bandits.
Okay, but is it not like that? Like if the query is same, shouldn't you choose the algorithm once because in the same context there is a high chance?
The could change as time goes on.
Okay.
Yeah. So at every point in time, you could choose a different draft model, and you should choose a different draft model to explore the environment.
Okay. I mean, what I was thinking is if your like query is same in the same sequence,
yeah,
the context should be same. So then the draft model will likely to be the same, or is it not true?
Here we don't have the notion of context. It's like in contextual bandits.
Okay.
Yeah.
Okay. So in your result, do you actually see that different draft model is being chosen?
Yes. Different draft models are being chosen as time goes on.
Okay. I see. Okay. Thank you.
Yeah. So there are some mathematical challenges that we have to overcome. Either we overcome them or we put some assumptions, right? So one of the assumptions that we will make is to take care of the third problem, all right? That the tokens are generated auto-regressively. All right, so what we assume is this, what we do is to make this assumption called the stationary mean values assumption. We assume that there are k numbers such that the expected number of accepted tokens satisfies the following. Okay, so this is not exactly the IID assumption because it could depend on the past. Right, so this is the expected number of accepted tokens, y of ITT, right? These numbers here, mu of I, right, they stay the same throughout. So what we do here in the stochastic setting is we design a UCB type algorithm, not very fancy, all right? We design it such that the confidence radius is derived from the self-normalized bound. This is used in the study of linear bandits. All right, so this is not a very innovative algorithm, but the innovation lies in the fact that we are going to apply it to a new setting, a new application. So in addition to this, in addition to combining this linear bandit type technology with this assumption, we design the algorithm as an anytime version algorithm, meaning that it doesn't require the time horizon as an input. So I'm not going to walk through all the steps of the algorithm because to those who are familiar with it, this is very familiar. To those who are not, require some time to explain. But basically, it takes in a number of hyperparameter specifications, a history, and a confidence parameter. And it basically updates the statistics as per normal and designs a confidence radius based on some martingale type arguments, just like in linear bandits. Okay, and there are some UCB statistics, and we play the arm that maximizes the UCB. Okay, so what we can prove here is that under the stationary mean assumption, given any prompt and bandit configuration, the stopping time regret, that is a new quantity that we define, of UCBspec is upper bounded by, the important term here is that it scales logarithmically with the expected length of the prompt. But we are also able to identify some other interesting hardness parameters, which are of interest to bandit people. So the hardness parameter looks as follows. All right, so this is a hardness parameter that depends on the gaps. The gap between the ith arm, the mean of the ith arm, and the mean of the best arm. So it looks like this. All right, so this is very intuitive. The smaller the gap, the higher the hardness parameter and the higher the regret. Okay, so this looks very intuitive, but as an information theorist, I need to ask the question whether it is tight in any sense. All right, so here L is the maximum length of the generated token sequence, and I said it's usually small, so L squared, let's assume it's also small. So we are interested here in instance-dependent type lower bounds, and we are interested in seeing whether we can match this hardness parameter. Now, settings we can. And here what we are focused on is a particular distribution on 1 to L plus 1, which is, in particular, we are looking at this truncated geometric distribution. Okay. If we look at if we focus on the truncated geometric distribution, which is basically the geometric distribution, but beyond L plus 1, we collect all the s and we put it at L plus 1. Okay, so this is the geometric distribution, but we look at beyond L plus 1 plus 1. This was considered in the speculative decoding distribution. All right, so under some decoding strategies known as greedy decoding strategy, we can lower bound the regret of any algorithm, all right, and the regret grows as the logarithm of the length of the generated prompt sequence, and the multiplicative factor is given exactly by the hardness parameter, as you can expect. All right, there's a term here, but in cases where parameters lie in some empty interval, then the bounds match up to the log of the length of the generated prompt as well as hardness parameter. All right, so we are not able to match this L squared term, but we are able to match everything up to the hardness parameter as well as the length of the generated prompt. Here we have to consider a sequence of prompts as m tends to infinity. Otherwise, the asymptotics don't work. All right, so this is some lower bound on the stopping time regret. Now, in the study of bandits, one looks at stochastic bandits and adversarial bandits. It is not clear our new application whether it fits the stochastic setting or the adversarial setting, because it's a completely new playground for bandits. So it is prudent for us to look at another set of assumptions. Let's throw away all the stochastic assumptions and let's model the problem as an adversarial bandit problem. What do we mean by that? So let us assume that the length of the accepted tokens is fixed by the environment before the algorithm starts. It could be anything. All right, it could be anything. So this is analogous to the oblivious adversarial case in bandits. And a very natural algorithm that one can design is an EXP3 type algorithm. Okay. So here we make no assumptions on the distribution of the length of the generated sequence or anything. Okay. It is just a bunch of numbers. So under some assumptions that are too complicated to state, and using the greedy decoding strategy, prompt PT, and any bandit configuration, the EXP3 type algorithm to be made anytime, right? Satisfies a sublinear regret bound. An EXP3 type algorithm is an exponential weighting type algorithm that I'm not going to go through, okay? But it basically looks very much like the EXP3 type algorithm that you encounter in any bandit book. Here we need to estimate some statistics and we need to plug them into an exponential type estimator. All right, and we need to sample the draft model or hyperparameter question about comparing between algorithms. But there is a deeper question here. What is the best assumption that we can make on this particular language model setup? Should this particular problem in speculative decoding in large language models be modeled stochastically or adversarially? It's not so clear. So the purpose of the experiment is not just to compare between the performance of different algorithms, but also to understand the nature of this problem. So now let me go through the most interesting part of the talk, which is the experiments, okay? And I'm going to try to walk you through what sort of experiments we did, what are the different hyperparameters, and what are sort of improvements that we make, all right? So we have two target models. These are large models. And we have 4 benchmarks. Benchmarks are data sets, all right? There are 2 metrics. I told you that in theory, we minimize the so-called stopping time regret, but in the area of interest, people are more interested in the mean accepted tokens, all right? So it's better to report the mean accepted tokens or the throughput. These measures, the larger the better, unlike regret. We are interested in these metrics instead. So the mean accepted is an important measure. It focuses on the design of speculative decoding algorithms, and throughput is related to user experience, right? So we look at 2 different things, all right? Here in the first settings, we look at 4 different draft methods. So here there are 4 draft models. I've already mentioned a few like suffix 3 and eager 2. Okay? The other setting, I will talk about it later. I'll walk you through this line later on. But let's look at the first setting in which there are 4 different draft methods first. Okay? So here are the 4 draft methods in the vanilla method. These are the 4 existing draft models. So our algorithms are called EXP3Spec and UCBSpec. Okay? So let's just focus on the table above because there are too many numbers here. So these numbers, you should read it as the larger the better. And we can observe that, all right, UCBSpec performs the best across all. Eager 2 is the state of the art, and UCB performs better than it in terms of the mean accepted tokens and the tokens per second. What is also interesting is that UCB usually outperforms EXP3. What does this suggest? This suggests that this particular application seems to be more well-modeled using stochastic environment compared to adversarial environment. Adversarial may be too worst case or pessimistic for this particular speculative decoding problem. So an average case analysis coupled with reasonable assumptions might be more reasonable for results throughout. Okay, the same observations can be seen under large language model. You realize that these draft models are quite diverse in their qualities. So when I gave this talk 2 days ago, or 3 days ago, someone asked, well, if you choose draft models that actually perform comparably, right? Comparably, couldn't be that UCBSpec's improvement could be even better. Because what this suggests is that one draft model here seems to be significantly better than the rest because it's the SOTA, it's the state of the art. So is it that the UCBSpec heavily relies on eager 2? This could be a case, right? If you have one arm that is significantly better than the rest of the arm, very, very soon, you will pull that arm many, many times. And that could be the case. So if you can come up with certain drafters that are as good as eager to, then the bandit strategy could conceivably yield significant improvements. Here it yields some improvements, right? Some, right? 10% or maybe 5% improvement. All right, so I basically want to summarize what I said using these 3 lines here. The best throughput performance is always achieved by the proposed algorithms. The proposed method automatically adapts to different prompts, the PT, as they are the best fixed method. Okay, all these methods are fixed. You always use them. Fixed, it doesn't change. But if you change, like in bandits, do better. This is something that I emphasize, as the empirical performance of UCBSpec is better than EXP3. This implies that the real world scenario tends to be benign, stochastic, and if you assume worst case scenario, you are too pessimistic. Okay? All right, so I want to go through the second set of experiments. This is a little past, so let me walk you through what we are doing here. This is the second set of experiments. Remember that in my setting, there's this thing called L. L is the maximum length of the generated tokens. In the very first example on speculative decoding that I mentioned, L is equal to 4. But that could also be treated as a hyperparameter, right? We could draft 2 tokens instead of 4. We could choose not to use drafting at all. What is L corresponding to in that case? If we don't use drafters at all, if we just focus on using the target model and you have a lot of resources, L is equal to 0. All right, so that could be treated as a hyperparameter. We call that gamma. Gamma is a number that ranges between 0 and 4. All right, so that is a hyperparameter that we could try to play with as well. So here we fix one drafter, perhaps the best drafter, I don't know, and we fix one target model. And we vary the so-called speculation length between 0 and 4. All right? So every point in time, we speculate. What do you expect? What do you expect? As you go on and on, you expect that you can speculate more and more confidently. Then your speculation length after you have done lots of exploration would be longer and longer. But at the very beginning, you might want to try to be conservative and speculate less. But if you use a speculation length throughout, all right, you can get some performance. Let's see what is the best, whether bandits are actually useful. So I hope that this setting is meaningful and you understand. L is fixed, L is 4, and you could have different speculation lengths chosen by bandit algorithms. Okay, so I want to show you this picture. There's a lot of stuff going on here, so I'll walk you through it. So we have a big target model, LLaMA3, and we have one draft model, let's say eager1. Okay, so what this says is, okay, we have different gammas, which are the different speculation lengths. Oh, here on the x-axis, we have different prompts, 500 prompts. And we are going to sort the prompts from left to right based on the Oracle best throughput improvement. So these prompts are sorted just based on their improvements. There's no particular ordering in terms of their meanings, okay? All right, so you can see the UCBSpec is red. So generally, it has the best performance in terms of throughput improvement compared to if you use different speculation lengths. If you use different speculation lengths. So if you commit to one speculation length at the very beginning, you may do well for some prompts, but you will do very bad for other prompts. For example, if you commit to gamma equals to, I don't know, 2, you do just as well as Oracle for these prompts, but you do miserably for some other prompts. But UCB tends to be able to adapt to all different prompts here. That's the message that I want to convey. Okay, so we can adapt to different prompts and also different draft models here. So here, what I've illustrated is 2 different types of hyperparameters, speculation length as well as different draft models. Throughput improvement, I don't know. This one is probably the baseline, and this is the number of times improvement over gamma equals to 0, which is canonical decoding. So gamma equals to 0 is this gray line here. It is at 1. So 1 means you just use a target model, fixed target model. As I said just now, I did an experiment. What is canonical decoding, or just using one target model? It is gamma equals to 0 because you don't draft. If you draft 1, gamma equals to 1. Draft 2, you gamma equals to 2. Okay, gamma equals to 2 works pretty well for some prompts, but it works miserably for some other prompts. So we have 500 different prompts. Okay, so these are different prompts. You might think, what is the 500 prompt? Right? There is no semantic meaning to the 500 prompt, apart from the fact that based on the Oracle best performance, we place it at 500. Right? I know this looks a little bit confusing, but here are just different prompts. All right? This 500 prompt is that yields the highest improvement based on the Oracle best strategy, which is the UCB best strategy as well, very closely tracked by the red line. Is that clear? So this one basically tries to show you that regardless of whatever prompt that I use, UCB seems to perform well. Okay? We could actually draw this using a table of prompts, but then that would involve 500 lines. Okay, so this is another target model, and we observe the same behavior. This is a big model, this is a small model, and we have a certain number of prompts here, and UCB seems to perform the best for every different prompt. Okay, so let me just almost end here by mentioning a few possible extensions and limitations. So the stationary mean assumption, some people will criticize because it's stationary. All right? Because in prompts, you could change your prompt, you could change your target each time. So for example, in the very beginning, you might be interested in code debugging. Then your job may be different later on. So this mu here, the vector of mu's might change over time. So this could be restrictive, but it's strictly weaker than the usual IID assumption in bandits. Now, what we have tried are the basic algorithms you would find in any bandit book, suitably modified. But one can consider some fancier algorithms like KLUCB, which are asymptotically optimal. So that's better. The question then is, the concern is, if you try some fancier bandit algorithm, the implementation time of these bandit algorithms should also be considered in addition to the decoding time. They are extremely cheap. KLUCB requires solving optimization problem. Ultimately, we aim to reduce the wall time of the decoding process together with the arm selection rule. So we might want to be prudent as to what bandit algorithm to use. We know a lot about bandit algorithms, and we might be tempted to use some of these tools in our problem. But we need to be concerned about the wall time. All right, so this brings me to the end of my talk today. We introduced this framework called BanditSpec, a bandit-based training-free algorithm for adaptive speculative decoding. We developed two arm selection strategies, one assuming a stochastic environment and one assuming an adversarial environment with some theoretical regret guarantees. More importantly, we demonstrated significant empirical improvements in decoding throughput. I've already mentioned that you could play around with other bandit strategies, but there's always a trade-off between simplicity and efficiency. Right? Thank you very much.
So when you have different algorithms to evaluate through UCBSpec, you need to get the probability distribution for each of the algorithm.
Yes.
Right. Now, let's say you had like 4 draft models. So let's say, so what are the sizes of the draft models? Like 1 billion or maybe 2 million?
No, they are not very large, like only 70 million.
But then
negligible.
Yeah, but then if you use 4 of them, then again you have
negligible, still negligible.
Okay.
4 multiplied by 70 million is negligible compared to billions, right?
Okay.
Yeah.
And what kind of GPU did you use? So I am guessing you have multi-GPU system.
Yes. That I cannot really comment on because I didn't run the experiments. But we needed our industrial partners to run this. I was more interested in the theoretical aspects, like how to set up the regret and stopping time analysis.
So my comment is, yes, I agree it is negligible, but if you have, let's say, a single GPU system,
yeah,
then even if your like draft model size is negligible,
yes,
you cannot run them parallelly. So I am guessing you are running those draft models parallelly to get the
possibly,
distribution.
yes.
Yeah. So
you need multiple GPUs.
Yeah, but in
this is available, right? Multiple GPUs, even my group.
Yeah, but in single GPU system, this will be a memory bound.
Sure, yeah. But
okay.
In order to run these, we need multiple.
Okay. Another question is, can you go to one of those where you
this picture?
Yeah.
Maybe
So
this picture.
is the x-axis different prompt
Yes.
or like single query over number of tokens? Because I can see 512 is the total size of the x-axis.
This is the prompt. No, these are different prompts.
Okay.
Yeah.
So I mean different
prompts.
prompt of prefills, like prefill with 40 tokens, 80 tokens, something like that.
No, these are just the prompt. These are the different prompts with indices from 1 to 500 plus.
Okay.
Yeah.
Okay. Thank you. Hello.
So I concluded that from the empirical results that stochastic case is better than the adversarial case.
Yes.
But is the empirical result enough to conclude that? Because we can design some different kind of algorithm, like different from EXP3, then which may perform differently.
Yeah. So the initial experiments, these 2 sets of experiments based on EXP3 and UCB somewhat suggests that the speculative decoding environment resembles more of a stochastic nature than adversarial nature. We cannot definitively conclude, but there is some compelling evidence that UCB is better than EXP3. Of course, we have not looked at all possible algorithms for the adversarial case. Perhaps EXP4 will be better.
To understand the computation of the probability in the large model, 8 billion model, how do you compare that? Can you tell something about, you've now gotten a draft model, put out the next X, and you're computing the probability to accept or reject.
Yes.
But the computation of the probability compared to the generation, can you tell something about how long it takes to compute in the large model? That's one question. Second question is related to Metropolis Hastings algorithm. I see some connection, but I'm still not able to place my finger on what the connection is. The acceptance rejection algorithm seems to be very similar to that. So are you aware of any connection?
Okay. So maybe I can go back to the computation of the probabilities. Yeah, probably here. So after the draft model drafts a certain number of tokens, say 4, then these probabilities should be computed, P and Q. Now, computation the computation of these probabilities should be less than that of generation, sampling. Otherwise, this step here will incur the same cost as that of using P to generate. This I think is significantly less than generation. Computation is significantly less than generation. Yeah, because otherwise this step here of acceptance or rejection, why don't we just use the target model instead, right? Yeah. Yeah. The second question is Yes. 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 So there is certainly some connection. This formula here is not plucked out of thin air. It is meant to ensure that the distribution of speculative decoding is the same as canonical decoding. Very much like Metropolis Hastings also preserves some form of the distribution of Markov chains in that way. Yeah.
Just a question, like, do we need an assumption that all the at least there exists one draft model that is consistent with P?
No, we don't have to. All draft models could be very bad. Okay, but then the situation would not be that good. All right, so like this is like a bandit question, right? Do all the arms have to be good? No, but we try to do our best given what we have.
Okay.
Yeah.
I mean, we have shown that we may not get any drop in the accuracy, and that's why I was wondering, do we need such assumption? Because we said that probability distribution that we are going to get using P versus what we are going to get with a combination of Qs are the same. Let's say P showed, right? In the previous report.
Uh,
Oh, the right, next right, the last one.
here.
Yeah, the distribution.
Yeah, so this is for fixed draft model, right? So if you consider our bandit setting, you could have a bunch of draft models. Some could be better than others. But here what we are trying to do is, okay, this is just in terms of the quality of the prompt, all right? But in our particular setting, we are interested in the stopping time. That is a different metric. Now, if you have some good draft models and you have some bad draft models, you want to try to look at choosing some good ones, exploring the good ones and bad ones, maybe a combination of them in order to improve the stopping time regret. But this property is always ensured.
Okay. And just one more question, in the data set that we used for validation or doing the experiment.
Yep.
Does it have different domains? By domains, I mean, let's say if we want to evaluate it on maths, we could have domains like algebra, calculus, probability, like this. So do we have different domains in the data sets, or it's like a...
Oh, okay. So I believe this data set, like SpecBench, has a bunch of different domains.
I see.
Yeah.
And it's still the UCB performance.
Yes, a bunch of different domains, a variety of them, not just math, not just coding.
Okay.
Yeah.
It's a mix of all.
Mix of them. Yeah.
Any more questions? I hope Professor has addressed all your clarifications. If you want to connect with Professor, please feel free to do so by having a cup of tea at our coffee hut. Thank you all for joining. Thank you all and have a great day.